So in this lecture, we are going to discuss about three-phase full-wave uncontrolled rectifier. So in case of full-wave uncontrolled rectifier, it contains 6 switches like a bridge. Each leg contains 2 switches. So let me name the switches as D1, D3, D5 are the top switches. D2, D4 and D6 are the bottom switches. And here the top switches are connected in this case, the top switches are connected in this case, they are connected in the common cathode connection. So the top switches D1, D3, D5 are connected in the common cathode connection. Common cathode connection. Common cathode connection. So similarly, D4, D6, D2 are connected in the common anode connection. Common anode connection. So these 3 anodes are connected at same point, common anode connection. So as we know that in common cathode connection, the device which is having the most positive voltage, that device will get forward bias. For example, in case of D1 and D3, D5 are connected to the A, B, C phases respectively. For example, if B phase is most positive, so in these 3 devices, if B phase is most positive, what happens? The D3 will be forward bias. So which phase voltage is most positive, the corresponding device will be forward bias. Now let me observe here. So it is a 3-phase waveform. So as we know that VA equal to, so the VAN equal to Vm sin omega t. Vm sin omega t. So VB equal to, so Vm sin omega t minus 120. Right? So it is VB should start from 120 degrees. VA will start from 0 degrees. So it will lag A phase by the 120 degrees. Similarly, VC will be lag A phase by the 240 degrees. Sin omega t minus 240 degrees. So by this assumption, so by these phasor values, so we have drawn the 3-phase waveform. So we have seen how to draw the 3-phase waveform. So from that, so I have drawn the 3-phase waveform. Now if you observe here, the VA phase, the VA will be most positive in between the 30 to 150 degrees. If you observe from 30 to 150 degrees, VA will be the most positive when compared to the remaining phases. 30 to 150 degrees. So what happens during the period of 30 to 150 degrees? 30 to 150 degrees, VA is most positive. In common cathode connection, if VA is most positive when compared to the remaining phases, so the corresponding device will get forward bias. That is, D1 is connected to the A phase, so the D1 will be forward bias. D1 will be forward bias. So here I will represent the same. So the D1 will be forward bias in between the 30 to 150 degrees. Similarly, VB will be forward bias. So VB will be most positive from 150 degrees to 270 degrees. So 150 to 270. So VB will be the most positive when compared to the remaining phases. So the D3 will be forward bias. Similarly, VC will be most positive. So VC will be most positive. So in between the 270 to 360, and so from 0 to 30 degrees also, the C phase, that is blue color, will be most positive when compared to the remaining phases. So when compared to the remaining phases, 0 to 30 degrees. So the device is forward bias as D5. So now let me represent these devices. So from here to here, it will be the D3. So from here to here, it will be the D5. So here also, in this gap also, it will be the D5. Right? Now let us represent remaining phases. Let us represent the remaining phases. So in the common anode connection, what happens? So D2, D4, D6 are connected in the common anode connection. so that the phase which is most negative will get forward bias. The corresponding device will get forward bias. So if you observe here, from 0 to, so let me start with 90 degrees. Let me start with the 90 degrees. So from 90 degrees to 210 degrees, what happens? The blue color, so that is C phase will be, so the blue color line will be the C phase. The C phase should be most negative. C phase is most negative. C phase is most negative. When C phase is most negative, so which device will forward bias? In these three devices, if the C phase is most negative, C phase is connected to the D2 terminal, so that D2 will get forward bias. D2 will get forward bias. So from here to here, D2 will be forward bias. So similarly, from 210 to here 330 degrees, 210 to 330 degrees, what happens? So the red color is the A phase. So red color is nothing but the A phase. So A phase will be most negative. A phase is most negative. Now you can answer, when A phase is most negative, which device will get forward bias? When A phase is most negative, the corresponding device will be the D4. So the corresponding device which is connected in the common anode is D4. So it will get forward bias. So similarly, from 330 to 360, 330 to 360 and 0 to 90 degrees, the device is, so that is B phase is most negative. If B phase is most negative, D6 will be forward bias. D6 will be forward bias. So from here to here, D6 will be forward bias. So from here to here, so it will be the D4. So in this gap, it will be the D6. So now, so we have found which are the devices are forward bias based on the common anode connection and common cathode connection. So up to here we are clear. Now let me simplify this circuit. So how I can simplify this circuit? So here, if you observe, to find the output voltage, so I will simplify this circuit into the simplest manner. So that is, so if you observe A and B and C, so because of the maximum positive voltage, these three devices will be forward bias. So that these three devices will be called as the positive group, and the bottom devices are called as the negative group. Because of the maximum negative voltage only, so it will get forward bias. So it will be the negative group. So negative group of the thyristors. So the positive group of thyristors are D1, D3 and D5. And the negative group thyristors are D4, D6 and D2. So this, let me write a simplest form of this is the simplest form of the circuit. A phase, when D1 is connected, A phase is connected to the positive. When D4 is on, A phase is connected to the negative. When D1 is on, A phase is connected to the positive of the output voltage, and when D4 is on, what happens? So A phase is connected to the negative of the output voltage. So these three are the positive group of devices and these three are the negative group of devices. Now let us find the output voltage. For different switching patterns. For example, what are the possible switching patterns here? So here diode or thyristor, whatever it may be the thing. So here, whether it may be the thyristor or a diode, here we will use it as a switch. Its function is simply a switch. So when it is forward bias, if it is diode, when it is forward bias, it will get into the on position. If it is a thyristor, the forward bias, in addition to forward bias, we need to supply the gate pulse. So it will be in the on condition. So here the positive group of switches are 135, and negative group of switches are the, so let me represent as a D1, D3 and D5, D4, D6 and D2. Now this is the simplest form of the circuit. So what are the possible combination? So after positive group, these two switches can be on, and 1 and 6 can on, 1 and 2. So 1, 4, 1, 6, 1, 2, 3 4 3 6 3 2 5 4 5 6 and 5 2. So for this possible combination, we need to find the output voltage. We need to find the output voltage. How we can find the output voltage and current direction? Now we will see here. For example, let me take the first combination. In the first combination, what happens? 1 and 4 switches has to be on. So I will take the 1 and 6 first. 1 and 6 switches, when 1 and 6 switches is an on condition, the diode will allow the current only in this direction, right? When 1 and 6 switches are in on condition, so what is the current direction? The current direction will be like this. The current direction will be like this. So the current direction will be like this. So the current direction will be like this. When 1 and 6 switches is on, the current direction is same as assumed direction, that is I naught is positive. So when 1 6 switches is on, what is the output voltage? So the A phase is connected to the positive of V naught and B phase is connected to the negative of the V naught. So output voltage is equal to VA minus, so here like VA minus VB. So output voltage is equal to VA minus VB, so that it will be equal to VAB. So that it will be equal to VAB. VA minus VB equal to VAB. When 1 and 6 switches is on, output voltage is equal to VAB. For example, if 3 and 4 switches is on, what happens if 3 and 4 switches is on? So now let us look at 3 and 4 switches. So if 3 and 4 switches is on, let me close the 3 and 4 switches. So understand it clearly so that you can understand everything. So here 3 and 4 switches is on. What happens? The current flowing from the B phase to, so here it will come, current will come like this, and 4th switch is on, so that it will go into the A phase. So from this, A phase is connected to the negative and B phase is connected to the positive of the V naught. So what about the output voltage? When 3 and 4 is on, so what happens? The output voltage is equal to, so the output voltage is equal to VB minus VA. So which is equal to VBA. So every time we need to close the combination and we need to find the output voltage. But, so if you observe this type of analysis, so now follow this circuit. So follow this circuit. So this is the simplification of circuit, that is A, B, C phases, the positive group of 1, 3 and 5 and the negative group is the 4, 6 and 2, right? This is the simplification of circuit. So for this simplification, let me find the output voltage. For example, if 1 and 4 is closed, what happens? If 1 and 4 is closed, VA minus VA, both are connected to the VA. So what is the condition? So it will be the 0. VA minus VA equal to 0. If 1 and 6 is closed, so it will be the VA is positive, B is negative. So VA minus VB, that is VAB. So if 1 and 2 are closed, A is positive and C is negative. So it will be the VAC, right? So again 3 and 4. When 3 and 4 closed, A is connected to the, B is connected to the positive and A is connected to the negative. So it will be the VBA. When 3 and 6 are closed, what happens? B phase VB minus VB. So it will be the 0. When 3 and 6 are closed, it will short circuit the load. So that the output voltage will be the 0. So next, when 3 and 2 closed, now you can fill the remaining combination. When 3 and 2 are closed, 3 is the B is positive and 2 is negative. So it will be the VBC. When 5 and 4 are closed, so it will be the VC minus VA. So it will be the VCA. When 5 and 6, VC minus VB. So it will be the VCB. When 5 and 2, so 5 is connected, so positive is connected to the C phase and 2 also be connected to the C phase. So VC minus VC, it will be the 0. It will be the 0. So this is how we can find the output voltage with this table. Even without observing the circuit. So if you know this table, so if you know this simplified connection diagram, so you can write the output voltage expression for the different combinations. for the different combination. Now let me find the VD1. Let me find the VD1 here. So VD1 is nothing but voltage across diode D1. So VD1 is the voltage across diode D1. So let it be the VD1. VD1 is the voltage across diode D1. So how I can find the voltage D1, voltage across D1? So when D1 is in on condition, so what happens when D1 is in on condition? When D1 is in on condition, the voltage drop across switch is equal to 0. So when D1 is in on condition, it will be the 0. So now, when D1 is in on condition, it will be the 0. So when D1 is in off condition, there is a possibility of either D3 or D5 is in on condition. So when D1 is in off, D3 is in on condition. So what about VD1? So VD1 equal to 3 is in on condition and D1 is in off condition. During that time, so here B is connected to the negative and A is connected to the positive. So it will be the VAB. Now we will see when D1 is in off condition, D5 is in on condition. What happens? D5 is in on condition, D1 is in off condition. Now we need to find the VD1, voltage across diode D1. So the C phase is connected to the negative of the VD1 and A phase is connected to the positive of the VD1. So it will be the VAC. And these three are the possible conditions, right? D1 is in on condition, VD1 equals 0. D1 is in off condition, D3 is in on condition. So it will be the VAB. D1 is in off, D5 is in on, it will be the VAC. And if you know this analysis, you can draw the output voltage as well as the voltage drop across the device for the full wave rectifier circuit, that is any circuit. So if whether it is uncontrolled, whether it is fully controlled, whether it is semi-controlled, these analysis is sufficient to draw the waveforms across the output voltage as well as the diode. Now let us go into the topic. So as we have seen, D1, D3, D5 are the positive group of thyristors. Let me represent the D1, D3, D5. So the D1 will conduct from here to here, right? So we have seen that D3 will conduct from here to here. So D5 will conduct from here to here. Similarly, D2 will conduct from, so let me represent with the other color. So D2 will conduct from here to 90 degrees to D2 will conduct from here to here, right? So D4 will conduct from here to here. So in this gap D6 will conduct. Now observe here. So from 0 to 60 degrees, D6 will conduct from here to here. So if you observe here, from 0 to 30 degrees, what happens? D5 will conducting. D5 is conducting from 0 to 30 degrees. So here, in the bottom line, 0 to 30 degrees, the device is D6. So that from 0 to 30 degrees, it will be the D5 and D6. So after 30 degrees, D1 will get into the conduction state. But at this instant, D6 will off and D2 will be in the on condition. So from here to here, the combination will be the D1 and D6. So the next combination will be the from here to here. So D2 is in conduction state. Here D1 is in conduction state. D1, D2. So from here to here, it will be the D3. Now D3 will start into conduction state. So still D2 will be in the conduction state. D2 and D3. So again from here to here, for every 60 degrees, there is one combination. So still D3 is conducting up to here, right? So the device here will be the D4. D3 and D4. So from here to here, it will be the, so D4 still conducting here. So the D5 starts conducting. So it will be the D5 and D4. So D4 and D5. So again here the D5 and D6. D5 and D6. So now let us draw the output voltage for this combination. So 0 to 30 degrees it will be the D5 D6. From 30 to 90 degrees it will be the D1 D6. So similarly, so the next combinations will be like this. So now we need to draw the output voltage. So how we can find the output voltage? So from the table we can find, right? So A, B, C, simplified connection diagram, that is plus and minus. So 1, 3, 5 devices, 4, 6 and 2 devices. So now when I will start from here. When D1 and D6 are conducting, so what is the output voltage? A is positive, B is negative. So it will be the VAB. It will be the VAB. Next, when D1 and D2 will be the VAC. Right? So D2 and D3. So from here to here it will be the VAC. Next, D2 and D3. So it will be D3 will be the VB. So it will be the C. So it will be the VBC. Again D3 and D4. So D3, D4. So it will be the VBA. So VBC. So from here to here it will be the VBA. So the next one is D4 and D5. So D5 is C is positive and 4 is A. So VCA. And here it will be the VCB and here it will be the VCB. Now find for the one cycle. Now if you find for the one cycle, so it is sufficient. You can find for the, so it will repeat for the remaining cycles. Now let me find for the one cycle. So here, so from 30 to 90 degrees, I will find 30 to 90 degrees. So at 30 degrees, at omega t equal 30 degrees, what is happening here? VCB is ending here and VAB is starting. So I need to find both VCB as well as VAB. So how I can find the VCB at 30 degrees? VCB at 30 degrees equal to VC minus VB. So C phase is blue color. So that is VC. C phase is blue color and B phase is yellow color. So VCB equal to, so VC minus VB, that is 0.5 minus of minus 1. So it will be the, so here it will be the 0.5 is the VC. VC value is 0.5. So and it will be the minus of minus 1. So VB value is the minus 1. So it will be the 1.5. So let me represent the point 1.5 here. So it is the 1.5. So now if I find the VAB, so VAB also the same value. So VAB also we are getting the 1.5. So VAB also 1.5 because A is 0.5 and B is the minus 1. So 0.5 minus of minus 1 will be the 1.5 and this point will be the 1.5 into VM. So 1.5 into the VM. Now let us find the, so let us find at 60 degrees also. Let me find at 60 degrees also. So at 60 degrees what happens? So at 60 degrees I need to find the VAB. So A is here and B is yellow color. So that is 0.866 minus of minus 0.866. It will be the, so root 3 by 2 minus of minus root 3 by 2. It will be the root 3. So it will be the root 3. So definitely it is greater than, so this thing. So similarly if I find the VAB at 90 degrees, so VAB at 90 degrees, VAB equal to A is red color, B is yellow color. So it will be the again 1.5. So even if I find VAC, A is 1 and C is minus 0.5. So again it will be the 1.5. So even VAC also 1.5. So for one cycle it will be like this. For remaining cycle also, even if you find, so you will get the same waveform. You will get the same waveform like this. So, but for one cycle we need to find. So this is how we will calculate the. And we will draw the output voltage. So from the waveform you can draw the output voltage so easily. So no need to draw the line voltage waveform. So if you can find for one cycle, so it will repeat for the remaining cycle. So now, let me draw the VD1. So when D1 is an on condition, D1 is on from here to, so here, when D1 is an on condition, the output voltage is 0. The output voltage is equal to 0. So it is in the 0 line. So the output voltage is equal to 0. So the output voltage is equal to 0. When D1 is an on condition, the output voltage is equal to 0. So now, when D1 is an off condition, so here from here to here D3 is an on condition. From here to here D3 will be an on condition. So if you find the D3, so what is the output voltage? In case of D3, when D3 is on, so the output voltage, the VD1 is equal to VAB. From here to here it should be equal to VAB. So when D5 is an on condition, so it should be equal to, so when D5 is an on condition, it should be equal to VAC. So we need to draw the VAC, and here from here to here we need to draw the VAB. So how we can draw the VAB? So VAB is nothing but VA minus VB. So at this point, at 150 degrees, so VAB equal to VA minus VB. So both are VA minus VB are equal to 0. So at this point what happens? So VA is equal to VAB. So red line and yellow color line approaches at the same point. So it will be the, so VAB. So it is the 0. Next, at this point, so again, so at this point, so at the center of the line, so it will be the, so what happens? VA is minus 0.5 and VB is 1. So minus 0.5 minus 1, VA minus VB. So if I find at this point, it will be the minus 0.5, VA is minus 0.5. So at this point, so VB is 1. So it will be the, VB is 1. So minus 0.5 minus 1 equal to, so minus 1.5. So this point will be the minus 1.5. So if I find the next point, so at this point, so what happens if I draw the VAB? So again, when it will be the 0, so after 1.5, it should be reaches to the, this point will be the, so it will be the 0.866. So it will be the minus 0.866. So it will be the minus root 3. So minus root 3, it is reaches to the maximum value. So it is reaches to the maximum value. So at this point, ending point, we need to find the ending point here. So VAB equal to VA minus VB. So VA is, at this point, VA is minus 1 and VB is the minus 0.5. So it will becomes to the, again it will reaches to the minus 1.5. So at this point, we need to find the VAC also. So this is for the VAB. We got the VAB here. So now here let me find the VAC. So VAC equal to, so at this point VA minus VC. So VA is minus 1. So VC is same, minus 1. So at this point it is also same. So if I find the VAC at this point, so A is 0.866, C is minus 0.86. So again it will be the, so minus root 3. So it is 1.5 point, so it is the root 3. So it is 1.5 and it is root 3. So here again, so it will be like this. So 1.5, and at this point VAC equal to, so VC equal to 0.866, that is root 3 by 2. So it will be the 0. So again it will go to the root 3 by 2 point. So root 3 by 2 point, it is a root 3 by 2 point. So this is how we need to draw. It is a VAB and it is a VAC. So we can draw the VD1 also from phase voltage waveform itself, we can draw the VAB and VAC also. So from this, PIE V equal to the maximum value equal to, so root 3 into VM, root 3 into VM, PIV equal to, so root 3 into VM. So now let us find the output voltage. So here, if you observe here, it is in the 0 to 360, it is completing 6 cycles. So it is also called as 6 pulse converter. It is also called as 6 pulse converter. 6 pulse converter. So now let me find the average output voltage expression. So average output voltage expression. So average output voltage equal to average output voltage V0 equal to, so here it will be the, so the time period we should consider the 2 pi period, that is 1 by 2 pi. So here we are considering the 1 by 2 pi period. So and it is conducting for the, so in the total duration, so it is repeating for the, so 1 by, so 30 to 90, so it will be the 60 degrees. It is conducting for the 60 degrees and it is repeating in the nature, So now it will be, so here 0 to, we need to take the limits as 0 to, that is pi by 6, that is 30 to 90 degrees, pi by 6 to pi by 2. We need to consider the limits as pi by 6 to pi by 2. We need to consider the limit as pi by 6 to pi by 2. So in between the pi by 6 to pi by 2, so the period is, so it will be the VAB into d omega t. So observe here, so it is, we need to find the periodicity first. So if you observe, the periodicity will be the 30 to 90 degrees. For every 60 degrees, the waveform nature will be different, same. So here we need to consider the periodicity as the pi by 6, pi by 3, and we need to take the limits as 30 to 90 degrees. So that is 30 to 90 degrees, and here we need to consider the limit as pi by 3. So pi by 3. VAB into d omega t. So as we know that VAB is equal to, 3 by pi into, so integration of pi by 6 to pi by 2. So VAB equal to root 3 into VM, so that is maximum voltage of line voltage, into sine omega t. So we know that line voltage leads phase voltage, the corresponding phase voltage, by 30 degrees. So it will be the omega t plus 30 degrees into d omega t. So now let us find the output voltage for this. So the average output voltage equal to 3 by pi into 3 root 3 into Vm by pi into, so sine omega t plus 30 degrees equal to, integration will be the minus cos omega t plus 30 degrees. So limits are 30 to 90 degrees. So here, if I apply the limits as 30 to 90 degrees, it will be the 3 root 3 into, so Vm by pi, so into minus cos 90 plus 30, minus cos 120. So cos 90 plus 30 is sin 30, so it will be the 1 by 2. So plus cos 60 degrees. So it will be the 1 by 2 plus 1 by 2. It will be the 3 root 3 into Vm by pi is the output voltage for the uncontrolled rectifier. 3 root 3 into Vm by pi. So now we have drawn the output voltage across the output voltage as well as the voltage across D1. So this similar analysis, and this analysis will applicable for the 3-phase semi-converter as well as the 3-phase full converter also. So in the next section we will see the 3-phase semi-converter and 3-phase full converter. So by this simple equivalent circuit with the 6 switches.